Hello, my name is James Freerichs. I'm from Georgetown University, and today I'm going to tell you about pivoting the undergraduate quantum mechanics class to support training in quantum sensing. This is work that was funded by the National Science Foundation and by Georgetown University. But before I get started, I want to have a moment of silence in solidarity with the citizens of Ukraine. Thank you. So we're now in an age where we need to be thinking about teaching quantum information science, and quantum information science has three pillars. The first is quantum computing, and here I'm showing you an IBM quantum computer and an algorithm that would calculate the quantum phase estimation. The second pillar is quantum communication, and here on the left I'm showing you a quantum key distribution system, and on the right I'm showing you the very famous BB84 communication protocol. And the third leg is quantum sensing, and for this I've chosen two examples of the global positioning system on the left and the laser interferometer gravitational wave observatory on the right. Now, in spite of lots of efforts that people are having in introducing quantum computing into their classrooms, physicists really have the strongest overlap with the quantum sensing pillar. And I want to discuss to you how you can supercharge your quantum mechanics class to be able to be preparing students for future careers in quantum sensing. So the first thing that you should do in your class is to actually focus on conceptual ideas of superposition, entanglement, complementarity, tagging, and measurement. And there are a number of resources for this. Feynman wrote a beautiful text called QED in which he described very complicated properties of light using just arrows that you draw on a piece of paper. And this can even be extended from the things that he did into very complex experiments like a Hongou-Mandel experiment. And Daniel Steyer has a wonderful book in which he does a similar thing, but he focuses on Stern-Gerlach experiments. And this is a wonderful resource for that. And with Stern-Gerlach experiments, there's also a number of interesting experiments, including things like delayed choice experiments that you can do with it. And then Ed Taylor is a person who showed that both of these resources really benefit from using computer animations to animate and bring to life the illustrations that are in the books. And while I'm not going to have enough time to show you some illustrations in this talk itself that are animations that we've worked on in my group, I use a large number of different animations and simulations, on the order of about 50, in the class when I'm teaching conceptual ideas of superposition and entanglement and so forth. The second thing we need to do is rethink using the differential equation approach and instead focus on this method developed by Schrödinger to develop the material algebraically. What Schrödinger showed us back in 1940 was that you can extend the operator solution for the simple harmonic oscillator and also for angular momentum eigenstates to actually solve all of the solvable models that we work on in a quantum mechanics classroom. And once you get rid of the differential equations and you focus purely algebraically, you're able to make the course accessible to a wider group of people, and you actually develop skills that they'll find useful because they develop a sense of how to work with operators, whereas there are very few research problems that involve solving single particle quantum mechanics with series solutions, which is what we tend to emphasize when we teach it with the differential equations methodology. In addition to getting the energy eigenvalues, you can actually get the wave functions algebraically. This is actually work that has been initiated in my group over the last few years, where we've shown how you can get wave functions for a number of the exactly solvable models using just algebraic manipulations. The third thing is we are physicists. Let's emphasize experiments, not mathematics. So this is a set of experiments that I cover in a one-semester class at Georgetown. And I just want to go through a number of them because many of these are not experiments that you would cover in a typical, even year-long quantum mechanics class. So these include things like the Hongou-Mandel experiment, delayed choice experiments, the proton charge radius, how LIGO works, E2E spectroscopy, which is a way that you can actually visualize the wave functions of hydrogen in momentum space, quantum seeing in the dark, high precision measurements, Pickering-Fowler lines, single photon detection, and so forth. Now, Asher Perez wrote a wonderful textbook, not too appropriate for teaching undergraduates, but it's still a wonderful textbook. And he has a great quote in his chapter that starts on experiment where he says, quantum phenomena do not occur in a Hilbert space, they occur in a laboratory. So one thing we really want to make sure we get correct if we're going to be teaching quantum mechanics for future careers in sensing is how do experiments work? And we want to make sure that we actually teach quantum science, not quantum science fiction. So what do I mean by that? Well, the science fiction story comes from John von Neumann. So he came up with a theory for experiment which says the following. If I want to measure a quantum observable, what I need to do is I need to prepare the quantum state that's going to be measured. I need to entangle the state uniquely with the apparatus, so pointer states of the apparatus are correlated with the eigenstates of the measured operator. It needs to be unique so that every state, every possible state or every possible value that I could measure is correlated with a different pointer state of the apparatus. And then I either apply collapse at some miraculous point of measurement, which is an ill-defined concept, or I use decoherence because my classical system that is my measuring device is large, and the decoherence will fix the pointer position in order to do the measurement. Now, this is a very logical, very clear, and it really sounds like a great way of describing experiment. But there's one really major problem of this entire theory of measurement. And that is that I don't think there's a single quantum experiment that is done that actually operates this way. So we should not propose a measurement theory that has no basis in reality. How do we actually measure quantum objects? In most cases, what we do is we infer the properties by clever experimental setups. So let me give you an example. One really nice example is spectroscopy. I shine light into some sample, and then light comes out, and I then want to measure the energy of the light. How do I do that? Well, I diffract it off a grating, and I measure an angle. And from that angle, I determine the energy. So let's go back to von Neumann. Where is the entanglement? I don't think there's any entanglement in this. Where is the pointer? I don't think there are any pointer states either. Where's the wave function collapse? Well, if I am using a single photon detector or some other kind of detector, typically I am destroying the photons at the point of time of the detection. This is usually a destructive experiment for the photons, but many quantum experiments are that way. And the one thing that's nice about those kinds of destructive experiments is there is no ambiguity as to when the experiment occurred. It occurred when I destroyed the particle in order to count it. Spectroscopy falls into a wide class of quantum measurements that involve counting quantum particles. And these experiments do not obey the projective measurement paradigm, and they're often not discussed in textbooks. Now, let me ask you the following question, also related to measurement. How would you respond to this question? What variables can be measured in physics? Is it only the position of a particle that is always measured, and the rest of the variables are inferred from it? This is a question that was submitted to Quora. And I'm going to paraphrase one of the answers, which says dynamic variables, including position, momentum, phase, spin orientation, and polarization can be measured independently, but non-commuting operators cannot be measured at the same time. And I would describe this colloquially as, if it is a Hermitian operator, it can be measured, but it must respect uncertainty. Now, there's a number of things wrong with that statement, even if you're sitting in the audience nodding your head to that statement. First off, just because it's a Hermitian operator does not mean I have a clear way of measuring that operator. And as I mentioned before, uncertainty is subtle. In a single shot of an experiment, uncertainty does not apply at all. It only applies after I have done many experiments and I look at the fluctuations in the measurements. Now, isn't the detector located at some position? So isn't it always de facto measuring position along with everything else that it measures? Let's take a look at a beautiful example that does this. This is a time of flight experiment. Here we have some event that occurs at a particular moment in time that signals a clock to start. We then let the particle travel through free space to the detector where it's detected. We then divide the distance traveled, which we've already measured, by the time to compute the speed. And from that, we can get the momentum. But of course, at the instant of measurement, we know the position and the momentum of the particle at the same time because we measured it in a detector at a particular location. This does not violate anything in quantum mechanics. Time of flight experiments are done all the time. It's simply not true to say that you cannot measure position and momentum at the same time. Please don't tell your students this, even if it says it in many different textbooks. Quantum measurement is difficult and subtle. We should always describe precisely how it is done and never say it can just be done. We have a great opportunity to improve quantum mechanics instruction. This talk is a short talk, so I was only able to give you a really quick flavor of some of the ideas behind it, but there's a lot of interesting things that you can do if you decide to actually introduce and incorporate quantum measurement in your quantum mechanics class. I hope you'll come join with me and others who are doing this, and we can really improve the way that we teach quantum mechanics to our students. I'm going to just end with my acknowledgments. I got funding from the National Science Foundation at Georgetown University. The Center for New Design of Learning and Scholarship helped also fund and provide support for this project. I have some quantum mechanics courses on edX that show these different principles and how they work. And that's a lovely picture of the McDevitts. I'm an endowed professor at Georgetown University, and they're the people who endowed the professorship. And then I'll just end by showing you some different resources that you can go to look at further work that I've done in this area. And with that, I thank you for your time.